He's really right. I wish I could do. Right? Or is it I don't even hate him. I love him. He's not good at
Nope.
I like skepticism. I did not on Thursday. I like sentence. And like I really sat next to him with like spice bread and like
That was one day.
yeah, that thing was good.
That was good. Do you remember that?
I'm like thoroughly
Okay. All right. Oh gosh. Sorry, I'm running late this morning, y'all. Okay, Sarah B. Okay. Claire. Matt. Luke. Jaden. Emma. Liza, yeah. Stuart. Ethan. Manya. Olivia. Kashal. Diego. Darwin. Stuart, right? Okay. Darwin, though? No. Let's see, where did, oh, it's right here. Okay. Sean. Jules, right. Doa, right. Matthew, right. Colin, Emily, Rennick, Sarah T, and McKenna. Okay, is there anybody here whose name I didn't call? No? Okay, well, only 1 minute late. That's not as bad as I was afraid it was going to be. Okay. Okay. So here's where we were last time. We were talking about a particular calculation that is useful. The idea is that if we have a vector field representing the velocity of a fluid, which is, if you think about it, a pretty reasonable way to represent the flow of a fluid, right? Then we could reasonably say, the fluid's flowing like that. And if we've got some area down here, how much fluid is flowing through that area, right? So maybe this is a net and we're fishing. Maybe for some other reason, maybe this is air that's going through a screen, right? We don't know how much airflow there is going through a screen, or water flowing through a pipe, any number of possible applications. Okay. All right. So that said, how we compute it? Well, let's just ask, in some small amount of time, delta t, how much fluid actually flows through? And in the amount of time, delta t, the amount of volume that passes through is the volume of this parallelepiped. Right? Because when it first starts passing through, it's here, and then as time passes and the fluid flows, it kind of flows up like that. Each little piece flows up by some vector d. Okay. All right, and so the calculation of how much volume this is just kind of label the appropriate things in the diagram, and then play with it until stuff falls out. And so specifically, height times area. Oh gosh, it's when my forearm, I think it's like some little hair down here, my forearm touches the little tablet thing. Anyway, I'm sorry. So height times base is immediate. Right? That height is, well, it's a component. It's the component of that vector D in the direction perpendicular, right? So we're interested in the I don't really care how much the fluid is flowing along the area, right? I'm only interested in the amount that the area is, or that the fluid is flowing through the area, right? So it's only the height there that we're interested in. Okay. All right, so what is this D vector? And specifically, how do I compute its component in the in direction? Well, in is a unit vector by assumption. That being a unit vector, components are just dot products. Right? Does that make sense? Y'all okay? Y'all are okay? Okay. Dot product with a unit vector is how you compute components. That's easy. And then, okay, yeah, but no, wait a second. What is this D vector after all, though? Right? This D vector. Well, that's the displacement of the fluid, right? The fluid, when you start your time delta t, you were here, and then it's going that way because that's what the fluid is doing. And then after time delta t, it's there. It is displacement. So it's velocity times time. And of course, the fluid velocity is represented by F. So one step at a time, just kind of thinking through what we have in this picture. And here is our formula for this amount of volume. Is everybody happy with that? Okay, why did I compute the amount of volume that went through in time delta t? Well, because what we're actually interested in is volume per unit time. Right, so knowing the volume is nice, but if you want to know volume per unit time, if you want to know how much water is going through this pipe, if you want to know how much seawater is going through the net and inferring how many fish you're going to catch, the actual flow rate, right? Well, you take the volume and you divide by delta t, cancels that delta t that's part of the calculation we just did anyway. And sure enough, you've got an answer then, and it's just it's the leftover. It's just this part. Okay, and that tells you the flow rate. How are we doing on that part of the calculation? Okay. All right, so for whatever it's worth, this is called flux, and flux is useful for different reasons. I've done this calculation here in the context of a fluid flowing through an area and thinking in terms of the volume per unit time going through, because sometimes that's what we're interested in. Sometimes that's what the vector field represents. Record should show, though, that in fact we're interested in flux, namely this expression. For different reasons sometimes, right? Not all of them even having to do with fluids, as it turns out. So this is really a mathematical expression, and we're encountering this mathematical expression because of, well, it happens to come up in, with this first application we're doing of it. Okay, so kind of stands to reason, though, that if this represents velocity, then flux represents flow rate. Okay. All right. Okay. So now here's a different calculation. We started off by the vector field representing velocity. Let's now change the vector field. Let's suppose now that the vector field represents not velocity, but density times velocity. And why would you want to do that? I mean, for something like water that doesn't make any sense at all, well, okay, I mean, it seems like a silly thing to do if you're talking about water, because water has a constant density. So it's just hey, let's introduce a constant. Who cares? Constants come and go as they please. You can do it before the calculation, after the calculation, whatever. But here's the thing, not all fluids have constant density. Right, and so here's another fluid I like to talk about. I mentioned something about this last week. a fluid representing, let's say, you know, a swarm of mosquitoes or a flock of birds, something like that, right? You can think of that as a kind of a fluid. Again, kind of weird, but also perfectly reasonable, right? So you've got this flock of birds flying along. The density is not constant, right? So if you're interested in the number of birds that are flying through some surface for some reason, not that we're catching birds, right? But still, if you're interested in how many birds are going through a window into your house, for example, perhaps. The density of birds, you know, how many birds per unit volume matters a lot. Knowing that they're flying a certain speed is nice, but if they're really close together and flying with that speed, that's a lot of birds per unit time. The throughput, the quantity per unit time is large. If it's a low density, well, then they're still flying the same speed. There's fewer of them, right? So multiplying by density is a way that you could kind of imagine that it kind of feels like it ought to give you quantity instead of volume. And in fact, that's exactly what happens if you just come up here, right? And ask what the quantity is in some amount of time, delta t. Well, the quantity is going to be, volume times density. So you add on a factor of density, right? And that density is exactly what's going to factor in and be part of this F that now represents velocity times density. Right, so I think it's a healthy exercise to go through the calculation on your own. Again, this is going to be your model right here. You're going to kind of rip off this calculation here, but now let the vector field represent this and compute dm dt quantity. Here I'm using mass, but density comes in all sorts of forms, right? There's mass per unit volume. There's population per unit volume, population per unit area, all sorts of versions of it. But whatever the quantity is per unit time, and what you're going to find is that it is the same formula. Okay, so this expression, this thing, F dot N times A, flux means different things in different situations depending on what your vector field represents. And sometimes you're interested in this, in which case you want your vector field to be velocity. Sometimes you're interested in dm dt. Instead, you're not interested in volume, you're interested in quantity of fluid per unit time, in which case your vector field should be density times volume. Everybody good? Okay. All right. Okay, so moving along. The book makes mention of this. I'm not actually clear where we're going to be using this later in the course, if at all, but again, not everything we cover in this course is going to build up to later things we do in this course. Sometimes things are expected to come up elsewhere in your learning. So anyway, this is one of those things, and so it describes something called a flow line. And so the idea is if you have a vector field representing the flow of a fluid, right? So vector field, where the velocity is what the field vector is. And we've seen examples of this. Let me go back to one where we have a nice picture. Here's one, the stirred pot, right? And now imagine what would happen if you were to drop something into the fluid there, something that has the same buoyancy as the fluid itself. What would happen? Well, it's going to do what the fluid tells it to do. And while it's at this point, it's going to be going that way. But then, of course, the fluid takes a turn, and this is just going to follow along with the fluid. And in this case, if you drop something into the fluid there, it's going to follow a curve kind of like that. So how would we find this curve? Okay. So called a flow line. So how do we find that curve? Well, of course, x prime is velocity. This curve, we're trying to find x as a function of t. The derivative is the velocity. But velocity, you know, at a given point, wherever you might happen to be, at a given point, the velocity is what the vector field represents. So altogether, the way you're going to find this curve, you know, this path that we're looking for, this flow line, the way you're going to find it is to look at this system of differential equations here. And I know y'all haven't seen how to solve systems of differential equations yet, but that's all this is. We have, you know, 2, maybe 3 different coordinates in this velocity vector. There's an x prime, a y prime, and a z prime. Right. Each one of those is equal to, well, some formula, some function involving x's, y's, and z's. That's a system of differential equations. How to solve such things, if y'all are engineers, and if you're going to be taking next semester Math 353, that's something y'all will learn in that class. Okay. All right, are we good? All right. Okay, I've already given y'all this speech, but I'm going to say it again because I do think this is really important. So vector fields are a mathematical construction. We're going to study them as mathematical constructions, and you know the applications are not our primary goal; they're a secondary goal in this class to see some applications, right? But the applications themselves, that's you know, the physics department's job, the engineering school, you know, whatever. So I want to view the applications in service of the math as opposed to vice versa, right? In an engineering class, the math serves the engineering, right? Here, other way around. We're going to talk about applications largely because that will help us understand the math. And so there are some situations, just, you know, heads up, be aware. There are some situations, mathematical constructions, where understanding the vector field as a force will give you a really good visceral physical way of relating to the mathematical objects of interest. Right? So it's very important to be able to understand vector fields as representing forces like gravitational forces, electric forces, like we saw a little while ago. But there are other mathematical constructions where where visualizing the vector field as a force is kind of weird, and I'm not clear how that helps me understand it. But if you imagine the vector field as representing a fluid, then this fluid point of view on the vector field will help you understand. It'll give you a visual, something highly relatable to understand the mathematical construction. So I emphasize both the force point of view and the fluid point of view are really important to understanding the math involved here. So don't think of these as just, well, they're applications that I don't personally care about. No, they're going to help you understand the math itself. Okay. All right, pausing for questions. Pretty good. Okay, so section 3.4 is going to introduce here some ideas that that are going to be really, really important later in the course. When we get into chapters 6 and 7, these are going to be huge, right? These things here, and of course we've already seen gradient, but divergence and curl and the del operator are going to be really, really important when we get into chapters 6 and 7. It takes a lot to build up and develop the ideas that go into really understanding why divergence does what we're about to claim that it does, and why the curl operator does what we claim that it does. We are nowhere near ready to do that yet. There's a lot of other stuff we have to build up and develop first. That said, the book is making the choice to introduce these ideas now. So for now, what this is going to look like is I'm going to show you various formulas, and I'm going to make some completely baseless assertions as to what they do. Right, and I'm not going to be able to justify. I'm going to be able to give you some examples, some sort of like, consistent with my claims, but I'm not going to really be able to tell you why. And so anyway, it will give you the advantage of kind of knowing in some sense what chapters 6 and 7 are going to be about, but leaving an enormous amount of gaps. So anyway, don't look for the whys as much in this section, and accept my apologies for that. for that. Okay, so let's get started. Y'all remember the gradient, right? It's the vector whose components are made up of the partials. Okay. By the way, everything in this section is going to be three-dimensional. No two-dimensional. Well, some of the pictures I'm going to draw are two-dimensional, but all the actual objects involved are three-dimensional. Nothing more than 3, nothing less than 3. Okay, so another way you can think about this, this is actually pretty reasonable if you think. I mean, so there's F, right? You can think of it that this symbol here is, well, it's the various partials that we are applying to F. But that said, if I were to kind of remove F from the picture, I could think of this as being a thing on its own. I can think of this symbol by itself, not del F, just del, as being, this we'll call an operator, and it's something that's waiting for a function to act on, right? Just like you could imagine. Partial differentiation with respect to X is a thing. It's not physical. I can't point to it. I can't draw a picture of it, but it's a thing that if you apply it to a function, does something. And likewise, the del operator, same deal. Okay. So it's a little bit weird to have an operator that's actually a vector, and I'm going to recognize that, yeah, it's not, I mean, we're using the notation of a vector because what we will do with it will eventually become a vector, and it's going to behave. It's not actually a vector, though. So let's, don't worry about that part. This is just notation. Okay, we okay so far? Okay, so here's my first definition based on that object, and it's called divergence. Divergence is something that you can do to a vector field. You have some vector field F with various components F1, F2, F3. Divergence is what you get when you do a dot product of the del operator with your vector field. And so keep in mind, our vector field has these components F1, F2, F3. Divergence of the vector field means take these various partials and add them up. Which is, I mean, in other words, if you were to write down, right, if you were to write down F as a vector, here, let me do it like this. Here's that, and there's F. If you were to dot them, you can kind of see it happening. Well, I guess I'm going to do the X partial of F1, and then let's see, after that, we do the Y partial of F2, and then after that, we do the Z partial of F3, and there it is. Okay. Now, reasonable questions come up of, hey, wait a minute, that's not really a vector. Are you allowed to do vector stuff with things that aren't vectors? Right, excellent complaint. Right, and this is, again, this is a symbolic business. This is flashing back to, you'll remember when we first wrote down the cross product, right? And we wrote the cross product as a symbolic determinant. Technically, we're taking a determinant of something that isn't even technically a matrix, but Yeah, but if you write the formula that way, it's very compact, it's easy to remember, and it leads to something that actually is mathematically meaningful. And so if we accept it as just kind of a notational convenience, then yeah, it's kind of nice actually. And the same thing is happening here. Right. So granted, yeah, you can't, I mean, this isn't really truly a dot product because one of the participants isn't really truly a vector, but let's not worry about that. Okay. All right, so this is this thing called divergence. Again, I've already made my disclaimer. We do not have the tools to make sense out of this yet. We will when we get to chapter 7. For the moment, I'm just going to again make an absolutely bare assertion what this represents. Divergence, right, computed with this formula. What it represents is, well, you got your vector field. Imagine your vector field as a fluid. Divergence represents how much fluid is kind of generally flowing away from any given point in your domain. And let me draw some pictures here. So here's a vector field representing the flow of a fluid. This is a weird vector field. It's kind of going to the right up here. And then it's going faster to the right, higher up. And then you wouldn't, even faster the higher you go. Going always toward the right, but the higher you are, the more up you go, the faster you're going to the right. Does that make sense to everybody? It's kind of a weird vector field, but there it is. But then, of course, as you go lower, sort of continuing the pattern, it's going to the left. So anyway, that's just what this formula does. Y'all can compute right now the divergence of this thing. Now, again, this is a two-dimensional example, and we typically think about three-dimensional examples, but it's just much easier to draw the pictures here. But y'all can compute the divergence, right? The divergence is that sum, which is 0. And I claim that that kind of tracks with this assertion that we've made up here, that the divergence represents the amount of fluid that's kind of generally flowing outward from a general vicinity. Because if you look at a point here, like let's say a point right there. Well, there is, at that point, there is some fluid kind of flowing into that general vicinity. There's also some fluid kind of flowing out from that general vicinity. And there's just as much going out as there is going in. So altogether, grand total is the fluid kind of emanating generally outward away from that point. Not really. I mean, somewhat, but just as much inward as outward. So 0. So again, that kind of tracks, right? This is consistent with this claim. It doesn't prove anything, I emphasize. But anyway, this is what I claim we're going to eventually be able to see why. Okay. All right, another example. Think about this vector field. And here I did draw one three-dimensional. So that vector field we've seen before, where the field vector is the position vector. We know that that's kind of an outward flow. And not only is it outward, but the further outward, the further you are away, the longer the field lines are, right? Compute the divergence of this. First component, second component, third component. Take the various partials from the divergence, right? X partial, Y partial, Z partial, add them up. And here you get 3. Here you get a positive number. This 3 being positive is representative of a positive amount of outward flow. And again, I appeal to your sense of the physics of this particular flow. It's flowing out away from the origin, right? But more than that, it's not just flowing out away only from the origin. Let's look at a different point And let's look. So for example, let's say right here, at that point, this vector field, well, there is some, I need the pencil here. Let's switch the pencil. There is some fluid flowing in toward the vicinity of that point. There is also field representing fluid flow outward. And notice, being as they get longer, the further you go away, there's more flowing outward than there is flowing inward. So altogether, I mean, there's a plus and a minus, but the plus outweighs the minus. And so you've got a net outward flow away from that point, even not the origin. Again, consistent with the fact that the divergence is positive. Yes?
Would the divergence always be 3?
Yeah, that's the weird thing about it, is that even though the field looks very, very different at all these different points, yeah, that this particular vector field, as it happens, the divergence is constant. Yeah. And that's just how this particular field happens to end up. Yeah. Anybody else? Okay. Oh yeah. Mm-hmm.
So we're evaluating the divergence at the zero vector, like at the origin?
Well, I was initially, right? So the very first thing I did is I guess I didn't draw this, but I was pointing out that, oh yeah, I did write the origin. At the origin, that's why you asked the question. I'm sorry, I didn't notice that. At the origin, the divergence is 3. And so this, specifically refers to what's happening at the origin, but you get the exact same calculation no matter what point you look at. If you look at some other point over here, right, the calculation's identical, you still get 3.
Why does it end up being the same?
Yeah, it's just how this particular vector field is. Every vector field's different. This one, the divergence happens to be constant. And there's lots of vector fields where the divergence is constant, and most vector fields, the divergence is not constant. Yeah, this one just happens to be this way. Is that cool? Anybody else?
So you could
Yeah.
write that as X instead.
Yeah. Absolutely. Yeah, that's what my little X here is supposed to be. Yeah. Yep. Okay, so now let's try to visualize physically what would this represent. If I have outward flow away from, and then we'll just focus back on the origin, just at the origin. What does that physically mean? Right, if this was birds, well, that means that the number of birds is going to be decreasing over time, right? So it may be that there's lots and lots of birds, and that they're kind of, some of them are leaving, and sort of periodically, every so often a bird gets up and flies away, right? And generally the birds are leaving, and therefore the number of birds in any given region is decreasing. So that's one reasonable explanation, that the amount of the quantity of fluid, right, is decreasing. You can see how that this is kind of consistent with that. But here's another metaphor. You could think of this as the fluid is being created. Now the bird metaphor doesn't work very well there. How, do birds reproduce that fast? Not really. But so there's a different kind of a fluid that I want you all to start thinking about. It's going to be really useful when we get to chapter 7. And that is the fluid of photons. Right? So photons it's a physics thing. It's just a little particle of light, basically. So let's just think of it as light. Light is a kind of a fluid. So these light bulbs up here are spewing out photons and making it into our eyeballs, and that's how we can see the light. And anything else we see because a photon has hit it, bounced off, kind of, and then made it into our eyes. Right? So photons are a flow of a fluid. But there's lots and lots and lots and lots of them in this room right now. Right? So, I mean, from that point of view, thinking about fluids, this is a really easy metaphor, and that is, well, there's a light bulb at that point. That's where the fluid flow is coming from, is because there's light and fluid is being created. That's what light bulbs do. They create and emanate photons. So different metaphor. So the reason I bring up these two different points of view is because this is another thing that, depending on the circumstance, and depending on what we're looking at, and depending on what the parameters of the situation are, sometimes you want to think about divergence this way. And on the other hand, in different occasions, you're going to want to think about divergence this way. So it's not always going to be one or the other. And again, it's one of these deals where you can't just pick one and decide, you know what, I'm a density decreasing kind of person. Right? There are situations where that's not it doesn't really fit with the problem. Okay, pausing again. How are we doing? Okay, here's another definition out of nowhere. No warning, no context, because that's what this section is. I'm going to define something called the curl of a vector field. This is a weird formula. It takes the weirdness of the cross product formula and sort of steps it up a notch. Because the curl, it's a cross product where, yeah, you take the determinant of, and then you put the standard basis vectors across the top. But it's a cross product where the first vector in the cross product is, again, a symbolic vector, not a real, actual, honest vector. So this is a symbolic computation on a symbolic object, partly. Very weird formula. And again, we absolutely do not have the tools to make any sense out of this yet from the formula. To see where it comes from, to make arguments about why it should or shouldn't be interpreted in certain ways. We're not there yet. We will. Give us time. We'll be able to make sense out of this in chapter 7. Okay. So, with absolutely no justification, I'm going to make, again, an assertion. This thing called the curl of a vector field represents the amount and the axis. So this is two things. So first, how much, and second, around what a fluid is kind of, and you can say this in different ways. I said here, circulating. You might think of the fluid as rotating or spinning, or you can think of it as little tornadoes called vortices. Lots of different words that all kind of talk about the same thing. But nevertheless, this thing called curl is telling us these two aspects of this spinning, curling, whatever you want to call it, circulation. So by the magnitude of the curl vector, it tells you how strong of a tornado is this. And by the axis, by the direction that the curl vector points, it tells you around what axis the fluid is circulating. So it's a weird thing, but that's what it is. Again, no justification. Okay, so let's see an example. And the first example, I like to start off with examples where the object in question is not happening. So here we're talking about the curl of this vector field. Now you can draw a picture of it, and it's we haven't seen this vector field before, but it's a vector field that it's always pointing in the x direction. And the amount that it's pointing in the x direction is, well, x. Okay, is that cool? All right, so to what extent does this represent a circulation? To what extent is this vector field, to what extent is this a stirred pot? To what extent is the fluid kind of turning? Or if I were to, have a perfectly balanced balloon that I just kind of waft into, if this represents air that's flowing and I toss a balloon into there, is that balloon gonna be made to start spinning around in some direction? Not really. It's just going to move, but there is no kind of curling or twisting or circulating happening here at all. That makes sense? So, and compute the curl, you will get 0. By the way, now this is a calculation that, you do have to actually do. You have to actually take the vector field, put it in here, compute it up, right, to see what you get. But I claim that if you do that, you will get 0. Yeah.
What did you see the magnitude of the curl represented again?
So the magnitude represents how much of a tornado is there, and the direction of the curl tells you around what axis the tornado is spinning. So here the magnitude is 0 because there's no spinning. Yeah. Okay. Okay, here's another one. Now this one we have seen, not exactly here. This is sort of a 3-dimensional version of one that we've seen before. This is the stirred pot, kind of a 3-dimensional version of the stirred pot. If you think about it, most pots are 3-dimensional. Right? So now what I drew here, again, the picture would become a nightmare if I were to draw all of the vectors sitting on top up here. It would just become a cluttered mess, right? So I've only drawn just down here in the XY plane just to try to keep it relatable. Nevertheless, I appeal to your intuition that this stirred pot, there we've got a little bit of a tornado situation here. It's flowing around a vertical axis, right, to some degree. And does curl detect that? Well, yes, it does. Compute the curl, yada, yada, yada. 002, which is vertical. So the verticality of the curl is indicative of this vector field flowing around that vertical axis. And the magnitude being 2 is a measure. We can't make units for this, but it is it's a measure in some sense of how strong is this tornado. So in this case, not super strong, but it's non-trivial. Yeah. Okay. All right. Now, another example. I think this one's really interesting. A lot of people would look at this vector field. Again, I'm only drawing just kind of, what's going on in the XY plane because the picture would become a mess otherwise. And even still, this vector field is kind of hard to kind of relate to it. But this is a lot like the vector field that we drew a few minutes ago. And let me see if I can scroll back to this one here. Right, so y comma 0. And remember, so everything's going horizontally, right? But it's moving slower when you're closer to the x-axis, and then the farther you get away, the faster it's going. Right, so this is kind of a, if you will, 3-dimensional version of that same thing. And again, kind of hard to draw a picture of. Okay, now a lot of people would look at this and mistakenly sort of think, oh, well, look at the field lines, the flow lines. All the lines are straight, despite my bad art here. Right, all the flow lines, all straight lines. How could there be any twisting or turning if the flow lines are all straight? But if you compute the curl, you take this vector field, I'll compute the curl, and the curl does not give you 0. The curl points down. So how does that make sense? How is that at least consistent with the idea that what curl measures is again this kind of circulation of the vector field? And I appeal as follows. Let's suppose that this was a fluid, right? Let's say it's water, perhaps, right? And imagine I take you've seen like if in the fall when a dead leaf falls on a river or on a creek or something, and the leaf just kind of flowing down the river, right? Sometimes the leaf is turning. Sometimes there's a twisting because roughly speaking, the leaf, let me see if I can draw a leaf here. So there's my dead leaf, right? And there is a small amount of current on that side of it, right? But there's a lot of current over on that side of it. It's being pushed harder on one side than it is on the other side. Altogether, it's being as it is pushed on the side, it's probably going to be turning. And in fact, this leaf would be turning kind of that way. Which, and the right hand is very convenient for this. If the thumb is pointing in the direction of the curl, then the fingers go in the direction that the fluid is flowing. This, let's see here, it's going around that way, and so down. All right, so that circulation tracks with this curl. And so I'm going to call that a victory for the curl. Right, curl does, even though the flow lines are straight, even though at a kind of a naive glance, we would say, come on, there's no circulation happening here. Well, yes, there is. Leaves turn on rivers, and as they should, and the curl figured that out. Yes?
Would you say like counterclockwise from below is like the same quickly as like clockwise?
Yeah, well, I mean, when you're in 3 dimensions, you really, the term clockwise and counterclockwise does not intrinsically mean anything because there's always this perspective problem, right? So this looks clockwise to me, it looks counterclockwise to you, right? So you always have to give a point of view when you use those terms. So I say counterclockwise from below, and another way to say that is the curl. I think I wrote this. Yeah, well, okay. I guess what I should have said here is counterclockwise as seen from the direction that the curl is pointing. Yeah, right. Is that good?
Yeah.
Okay. Anybody else? Okay. Yeah. All right. So this is just previews of things that we're going to talk about in much more detail in chapters 6 and 7. So again, we're not ready to be precise about this, but since we're talking about divergence and curl and such, and we have the formulas, we can do certain kinds of calculations, and I can observe certain facts about how these formulas work. And it turns out that some amazing things happen when you compose these various operators as follows here. So if you do the gradient operator there, and then the, I guess I'll just stick with this, and then the curl operator there, and then the divergence operator there. Seems like a weird thing to want to do, but look, you can, because after all, gradient of a function is a vector field, and the curl takes in vector field, so that, again, the Legos fit, right? Curl produces a vector field, and sure enough, a vector field is what divergence acts on and gives you a function. So again, the Lego pieces fit together here, and you may compose these. It turns out this is extremely natural, and a lot of beautiful observations can come out of this composition. So I'm going to tell you one of them. So I can say I said it, I'm going to say this is what's called an exact sequence, and don't worry about what that word means. What it means is what I'm about to tell you, but I'm going to tell you in much more sort of relatable terms. I have a favorite metaphor that I like for this. My metaphor involves thinking of the application of these operators as each taking a certain amount of time. So let's think of this as kind of a t-axis, and again, this is a metaphor, so don't hold me to anything rigorous here. Right? If you think of this diagram as representing the passage of time, if you have a vector field here, if you take its curl, and if you get another vector field there, I'm going to think of this as, okay, well, this vector field was alive. It's kind of, it's metaphor. And then after a little bit of time has passed, it's still alive. And then let's suppose you take the divergence of that, and then let's suppose you get the function 0. I think of 0 as death. Kind of, right? I mean, again, it's just a metaphor, but I think it's kind of relatable. And then here's another question we could ask. Suppose I have a vector field here. Reasonable question would be, is there a function whose gradient is that vector field? Maybe there is, maybe there isn't. If there isn't, then my metaphor is going to say, well, then this is the first instance where this vector field is alive, and therefore it's born here. So that's my little silly metaphor. If we have this picture here, right, then to me, born there, survived to here, dies here. And if you work with the metaphor, then a really amazing fact that encompasses like 8 different mathematical statements is all lifetimes are 2. Everything's a lifetime of 2. There's with one exception. Let's not dwell on the exception. But so, for example, if you have a vector field and you take its curl, okay, fine. That's all well and good. But if you have a curl, something that is a curl of something else, and if you take its divergence, oh, you will get 0, because that's a lifetime of 2. I guess I didn't write that one down, but anyway, lifetime of 2. So you will get 0 here. So the divergence of the curl of a vector field is 2. Here's another example. If you have some function and you take its gradient, you get a vector field. Fine, no problem. If you take, however, the curl of that vector field, that curl will be 0 because the lifetime is 2. Cool. And you can use this kind of the other way as well. Let's suppose that you have a vector field, and suppose you don't know where it came from. You got a vector field and you take its divergence, and suppose you get 0. What does that mean? Well, it couldn't possibly have been born here, because if it was born there, then the lifetime would just be 1, and everything is a lifetime of 2. So if the divergence is 0, that means that that vector field must be a curl of something to give it that lifetime of 2. Okay, so now, if you prefer, you can think of the whatever the 6 or 8 different versions of this as separate mathematical theorems that you can write down with algebra. They look something like this, and so this is just 2 of them, right? And that's fine, and good thing, I suppose. But I think it's much easier to remember them as these operators are composed in this way. Everything has a lifetime of 2, and then just infer accordingly as needed. Much easier. So anyway, that's how I like to think about it. And now let me be. I got to clean up my mess here. This does ignore regularity issues. So I mean, there are issues about what happens if there's a point where one of the vector fields has a discontinuity or something like that, or it fails to be differentiable. I don't want to worry about that. I want to assume everything in sight is as differentiable and continuous as you could possibly want it to be. And then there is the sad exception of constant functions, because if you think about it, if you have a constant function here, you take the gradient, you get 0. This is a lifetime of 1. It's a sad story. It's the only counterexample, though, to the general rule that all lifetimes are 2. Okay, cool. So that's a good ending point. And yeah, anyway, I'm going to call us done actually with section 3.4, and we'll pick up with chapter 5 on Wednesday. Y'all have a good day. Yeah, see y'all.
You know,